To get this lesson started, here is a warm-up problem. What is the smallest group in terms of its number of elements that you can think of? And please be sure to specify both the set and the operation of the group. So pause the video and see if you can come up with one, and we'll go over some of the examples afterwards. Well, here are some examples. Now keep in mind, every group has to contain an identity element. So that means every group has to have at least one element. Well, here's a group with just one element, a set containing the 0 element under addition. You can think of 0 as an integer, for instance. Here's another set with just one element containing 1 under multiplication. And we can think of 1 as a real number. Or the epsilon element under composition. And we can view that epsilon as a symmetry of a square, perhaps, or a permutation. And so every group has to have at least one element, the identity element, and we claim that we can get away with just one. And so let's take a look at one of these, perhaps the set with just the 0 element under addition, and actually verify that it is a group. And so here's our table. Let's build it. It's going to be very quick. 0 plus 0 is 0. And let's verify the group properties to make sure that this is in fact a legitimate group. And so, starting with closure. Is that set closed under addition? Yes, because the sum is the 0 element, which is in the set containing just the 0 element. So there we go. Associativity, well, there's only one case we need to check. Does 0 plus 0, parentheses, plus 0, equal 0 plus, parentheses, 0 plus 0? Can we move parentheses around? Yes, because both sides are equal to 0. Is there an additive identity element? Yes, 0 is there. And the fourth property, inverses. Does every element in that set have an additive inverse? Yes, because 0 is a self-inverse. When you add it to itself, you get the identity element. And so, rather a silly example, but the key point here is that, in fact, that is a group. And so the smallest group we can have is a group with just one element. And I'll leave it up to you to create a table for the other two examples to ensure that those satisfy group properties. And in fact, those tables will look exactly like the table for this set in some sense. And so it turns out that all groups with one element are essentially the same. And I'll let you ponder that idea a little more carefully as we work on today's classwork. And so once again, all groups with one element are essentially the same. Now please pause the video and work on day 9 classwork, and we will go over some of the questions and concepts afterwards. Let's start with problem number 2, which dealt with groups containing 3 elements. Now you built the following group tables, and we notice that those group tables are essentially the same. So here they are, the table for Z3 under addition. Here's a table for 3 elements from the symmetries of an equilateral triangle, epsilon, R120, R240, operation is composition. And here's an example from the permutation, 3 elements once again. And when I say that those group tables are essentially the same, here's one way to think about it. Let's say I were to color code the elements. And so the identity element could be in yellow. And so I'll color code the identity elements in yellow. And let's just color in yellow all the places where the identity elements show up. And we see that all the yellows show up in the exact same location in each table. Now let's color one of the non-identity elements. So here's 1, and I'll do that in red. 1 and 1, and 1 show up in those 3 spots inside the table. So here's R120, R120. And once again, they show up in the exact same spots. Kind of this top row, second column, middle row, first column, third row, last column. And same for sigma. Same exact spot. And then same for the other non-identity element. So 2, 2, and then all the 2's line up in that other diagonal from top right to bottom left. And same for R240. Top right, bottom left diagonal, and same for tau. There we go. And so the color scheme is exactly the same in those 3 tables. Now, let's try to build a general 3-element group and see if we can come up with that same color scheme. It's possible that we just got lucky with those 3, and maybe there's another 3-element group that don't necessarily follow that color scheme. And I want to go over that that's not going to happen, that every 3-element group will look exactly like those 3 tables that we see above. So how do we go about filling this table in? Well, the identity element, which I'll highlight in yellow. Oops, wrong color. So here is the identity element. We know that the identity element, when you multiply it by another element, it leaves them unchanged. So the top row should be epsilon A, B. And the first column should be epsilon AB as well. And so we have that much. So far, so good. How do we fill in the rest of the table? Well, we'll discuss this in the next slide, but let's focus on this spot right here. And I'll preempt this by highlighting that in yellow, and we'll see why in a moment. If you look at the row here, it already contains the element A in the row as one of the products. And so we know this can't be A. And if you look at this column that the yellow element is contained in, we see that B is already there. So we can't have another B in the same column. And so, well, the table, it's a group, so it has to be closed. So if it can't be A, and it can't be B, and it has to be one of the 3, well, the only option is the identity element. This is using what I call the Sudoku property, which I'll explain in the next slide. But if we just keep using that same principle, now if we focus on this middle row, it already has A and epsilon in it, and so it has to be B. And now if we go to this column, we have A and B already, so this has to be epsilon. And then if we go across, it's already got B and epsilon, so the last element has to be A. And now let's do the color coding. Where are the identity elements? Right there. And what about the element A, the first non-identity element? Well, they are right there. And what about the other non-identity B? Well, it's the top right to bottom left diagonal. And so once again, with the help of the Sudoku property, which I'll explain in the next slide more precisely, we were able to show that this has to be the table for any 3-element group. And so they all look the same if we just focus on the color and where those elements live inside the group table. And so the conclusion here is that all 3-element groups are essentially the same. And here's the Sudoku property, named after a popular number placement game. And here it is, right here. The property states that each row and column of any group table contains every element of that group G exactly once. So every row and every column of a group table contains every element of the group exactly once. And so let's just quickly recap how that property was used to generate a table for a 3-element group. So again, I'll go through this quickly because we did it in the last slide, but we started off with the identity element, and so there it is. And the key was coming up with this spot right here. Now, Sudoku property says that the second row has to contain every element of the group exactly once. Well, A already showed up in this row, so this can't possibly be A. And likewise, the Sudoku property says this column contains every element of the group exactly once. Well, B already showed up here, so this can't be B. And therefore, by the process of elimination, we have to have epsilon there. And then we filled in the table, the rest of the table, in the similar fashion. And so the Sudoku property, together with the fact that we have an identity element being represented in the first row and column, we use that to come up with this relationship AB equals epsilon. That's what we have right here. A times B equals epsilon. I will point out that this relationship, AB equals epsilon, in a 3-element group, that can be proved without relying on the Sudoku property as well. And so I'll leave that up to you as a challenge to think about. Next, we will provide a proof outline of the Sudoku property. And the complete proof is in chapter 9 of the textbook, and so I'll ask you to read it there. And here we're going to provide the big pictures. And so suppose we have a group called capital G, and it contains the identity, AB, little g, and this could possibly be an infinite group. And here's its group table. Again, this could be infinite, has all the possible products. And we'll focus on what I call row G, so this particular row. So let me highlight it. And so that's the row we're going to focus on. Now there's nothing, and let's talk about what it contains. So it contains G times the identity, G times A, G times B, G times itself. And so every possible product of the form G times another element from the group. Now, there's nothing special about that particular row. And so if we can show that row G satisfies the Sudoku property, then we can conclude that every row satisfies the Sudoku property. That takes care of the rows. How about the columns? Well, the argument for the columns is very similar to the argument that we'll make for the rows. And so I'll leave it up to you to come up with your own arguments for the columns, showing that every column satisfies the Sudoku property. So let's put our focus on row G. What do we need to show? Well, we need to show that this row contains every element of G showing up exactly once. In other words, we need to show a couple of different things. We need to show that all the elements in this row are different. So we can't have any duplicates. Now that tells us that every element of the group shows up in that row at most once. It doesn't show up more than once. But we also need to show that every element of the group actually appears in that row, that there are no missing elements in that particular row. Now that will tell us that every element of the group shows up at least once. And if row G contains every element at most once and at least once, then we can conclude that row G contains every element exactly once. And so in the next couple of slides, we'll show item 1 and item 2. So once again, here is our row G. And we'll start by showing that all the elements in this row are different. Now to do that, let's just pick any pair of elements in that row arbitrarily and show that those two are different. And if we can show that an arbitrary chosen pair have different elements, then we can conclude that they're all different. And so let's pick these two, GA and GB, and see why those are different. Now we already know that A and B are different. Those are two different elements of the group. So why does A not equal to B imply that GA does not equal GB? That's what we need to show. And so that's written right here. This amounts to showing if A does not equal B, then GA is different from GB. Now, there are lots of unequal signs here, and our go-to move, or my go-to move, when dealing with not equals, typically is showing the contrapositive. What's the contrapositive? It's if GA equals GB, then A equals B. But that's the statement of the left cancellation. We just cancel G on the left from both sides. And so we know left cancellation holds for any group. And therefore, item number 1, the elements in this row are all different, has been proved. Now, once again, here is our row G. And we need to show item number 2, namely every element of the group appears in this row. So to do that, let's pick an arbitrary element, say X right here. And we need to verify that X actually appears in this row. So that means if I want X to be in there, is there an element, which I'll call question mark for now, such that G times that element equals X? That's what we want. We need to make sure that there is some mystery element such that G times that mystery element equals X. And so that's where we are right now. How do we come up with such an element? How do we verify that such an element exists? Well, I claim that such an element is in fact equal to G inverse times X. Now, first of all, why is G inverse times X part of our group? Why is it in our original group? Well, this is a group after all, so if an element little g exists, then its inverse, G inverse, must exist as well. And we know X is part of the group. That's right here. And so we have two elements, G inverse and X, that are already part of the group. So by closure, when you multiply them, the product has to be in the group as well. And so we know this is a legitimate element of the group. Now we need to make sure that G times said element actually equals X. And so here's that calculation. In a nutshell, the G and the G inverse cancel each other out, leaving us with X. But let's go through the calculation. So if our mystery element is G inverse X, then we have G times that element. By the associative law, we can regroup, put the G and the G inverse together. That equals the identity, and so we're left with epsilon X, which is equal to X. And so in fact, we were able to come up with an element of the group such that G times that element is equal to X, which tells us that every element of the group appears in row G. Now, just one final remark. If you're wondering, well, how in the world did we know to come up with G inverse X? Please take a look at Chapter 9 reading. There's a proof know-how in there that explains how one would come up with such an element on their own. But with that, that's the end of this proof outline of the Sudoku property, and also the end of this lesson. So I will see you next time.